Swayam Prabha. Digital India. Educated India.
Hello and welcome to NPTEL video lecture number 4. Can solids be generalized? That is, can we come up with a single statement that covers valid solids of all possible shapes and sizes? We'll answer that question by studying topology of solids. Why do we need to study topology? Because description of solids is quite broad. They are plentiful and they come in a variety of shapes. With geometry, the form, which is the shape and size of a solid, is precisely laid. This is a constraint for us. Geometry does not give us the flexibility for generalizing solids. The boundary determinism theorem suggests that only closed connected surface B of V would seem sufficient to represent a solid in the Euclidean space. Looks like only bounding surfaces need to be considered. The effort is that a representation scheme is required that generically and efficiently models a solid of any form. One way is to ignore lengths and angles and study for the notations of continuity, connectivity, and closeness. That is, study the topology of a solid. With topology, one lets go of the specificity in size and shape and discusses only connectivity. We'll try to answer in this lecture if it is possible for us to describe solids generically. The next question: what is topology? Topology studies the patterns in geometric figures for relative positions without regard to size. In a sense, topology studies connectivity and the associated properties. Consider a paper band, for example. One can give this paper band any shape one wants. But primarily, it is a loop. Had this paper band been a rubber band, one could have even stretched it out. Topology is sometimes referred to as the rubber sheet geometry. When studying topological properties, bending, twisting, stretching, and other such transformations are allowed. Cutting, tearing, and gluing operations are not allowed. Consider this tennis ball. I can squeeze this ball any way I like to distort its shape. This is allowed. The paper band example again. I can bend it, I can twist it any way I like. But tearing is not allowed. Topology or analysis situs. Situs refers to site, perhaps, was initiated by Euler. Euler was challenged if he could solve the Königsberg bridge problem. This is the Königsberg bridge problem. This is the problem statement. Determine if the 7 bridges or edges in the city of Königsberg across 4 land patches, which are nodes, can all be traversed in a single trip without doubling any bridge back. In this slide here, these are the 4 land patches. And these strips in red they are the 7 bridges. In this figure here, the land patches are represented by nodes 1, 2, 3, and 4, and the other 7 bridges are represented by edges. Euler thought about this problem for a little while, and then he answered, no, it is not possible. Homeomorphism. This is one of the topological properties that solids share. Loose meaning of the term homeomorphic is of the same shape. Two solids belong to the same topological class if they have the same basic overall structure, even though differing much in details. Consider this cube, for example. This has a side of size A. This is a block of sides A, B, and C. So what I have done here is I have retained the size of one of the sides, and I have stretched the other two sides to lengths B and C. As you know, stretching in topological study is allowed, and that is the reason why this cube and this block are homeomorphic to each other. Likewise, what I have done now is I have distorted the internal angles as well. If you look at the cube and this distorted cube, this is also allowed in topology study. Therefore, even this distorted cube is homeomorphic to a regular cube. Question: is a sphere homeomorphic to a cube? The answer is, of course, yes. How is that so? Well, what one can do, since distortion is allowed, one can distort all the edges and all the faces such that they form equations of the spherical surface in part. The other way to look at this is consider this cube to be like a balloon. Inflate it in such a way that these edges, they happen to be placed exactly on the surface of a sphere, and so the faces, they happen to be placed exactly over the surface of a sphere. Therefore, once again, a sphere would be homeomorphic to a cube, and therefore all the other distorted versions of the cube. Now consider a hole drilled through the sphere. Is this solid homeomorphic to all the other 4 solids? The answer to this question is no, it is not. No matter what distortions you perform on any of these 4 solids, you will never be able to get this solid. Is a torus homeomorphic to a solid, a sphere, with a hole drilled in it? The answer is yes. You can distort this solid to get a torus and vice versa. A little more on homeomorphism. Let's look at how polylines or polygons fare. Consider this example, for instance. This is a quadrilateral with some internal point P. Since distortions, bending, twisting, etc. like operations are allowed, what I can do is I can straighten this angle. In a sense, I can make the internal angle between these two lines as 180 degrees, and I can also shorten the length of the resultant edge to get this edge. Are these two polygons homeomorphic to each other? The answer is yes, they are. Likewise, all simple closed polygons will be homeomorphic to each other, and in general they will all be homeomorphic to a circle. In other words, you can take any closed simple polyline and stretch it out to form a circle. Vice versa, you can take the circle and distort the periphery or the perimeter of the circle in any manner to get any closed loop. There is another observation that one can consider. Well, of course, all these figures are homeomorphic. If you consider an internal point P in all these polygons or closed loops, if you start from a point and say travel counterclockwise on the perimeter, you would observe that this point P will always lie to your left. Here as well, if you start from this point, say, and travel counterclockwise, point P will be towards your left. You have to come back to the same point from where you started. The point I'm trying to make here is that sense of orientation about a point P is maintained with all these closed polylines. Now, the question, is a straight line homeomorphic to any of these closed polylines? I can think of getting this straight line as follows. I can shrink this edge length to almost 0. I can shrink this edge length to almost 0, and so this. In the limit I do that, will I be getting a straight line? We get back to the paper loop example now, with 4 edges clearly visible. This is similar to the quadrilateral that you see in the slide. I can shrink this length, I can shrink this length, and I can shrink this length. But whatever I do, so long as I am not performing any cutting or gluing operation, if I stretch it fully, this will always be a loop no matter what. This will not become a straight line. To be able to make it a straight line, I have to perform a tearing operation. This is now a straight line. This is the straight line here. I had to cut the loop to be able to make a straight line out of it. Now, if you start from a point here and traverse the line and come back, let's say you do the same in this figure here. You start from this point, traverse through the line, stop, and come back. What you would see or what you would observe is when you had gone from bottom towards top, point P was towards the left, and when you traverse backwards, point P is now towards the right. So the sense of orientation about P, which was there in these closed polylines, is now lost. So we would say that a straight line is not homeomorphic to these closed polygons. We had mentioned before that the bounding surfaces are adequate enough to represent the respective solids. Surfaces are compact and connected topological objects. Each point has a neighborhood. A neighborhood is homeomorphic to either a plane, which is R2, or a half plane, which is H2. Let's see this figure here. It's a typical surface. You would see two kinds of points here. One would be the internal point, and the other would be the boundary point. For point P, draw any disk of radius r. What one can do is one can stretch it infinitely in all possible directions. For points Q and R, it is not possible for us to draw a full disk around it. It is only possible for us to draw or sketch a partial disk. Now this disk can be stretched only in a few directions and not all directions. For example, I cannot consider the neighborhood of R in this region here. This seems like an internal void. For which reason the neighborhood of the boundary points Q and R are half planes. Let's discuss surfaces and their boundaries. A closed surface is one that has no boundary. A cube, for example, it does not have any boundary. Another example, a sphere. Likewise, it does not have any boundary. A sphere with a hole drilled, no boundary. A torus, no boundary as well. All these are surfaces with no boundaries. Now consider a disk here. You can deform the disk to get a hemispherical shape. In that matter, both disk and the hemisphere are homeomorphic to each other. As you would realize, both of these would have one boundary. This is an open cylinder. This would have two boundaries. This is a rectangular plane folded into a cylindrical form. This shape will have one boundary. How many boundaries would you think are there in this surface? You're right. There are two. One would be the internal boundary, and the other would be the external boundary. Boundaries are like closed contours, both interior ones and the exterior ones. Now the question is, can a surface with boundaries enclose a volume to represent a bounding surface of a solid? The answer is no as of now, but you can perform certain closing up operations. Well, we all know that a generic surface may be composed of boundary components. Each boundary is homeomorphic to a circle. This is clear because you can modify, distort, bend, twist each boundary and get the shape of a circle. Now, if a disk also of a circular boundary is attached to all boundary components one by one, the result will be a closed up surface. In a sense, what we will get will be a surface with no boundaries and therefore a solid. It's like eliminating the boundaries one by one. The closing up operation preserves homeomorphism types. If surface S1 is homeomorphic to surface S2, S1 cap, the closed up surface of S1 will be homeomorphic to S2 cap, the closed up surface of S2. S cap refers to the closed up surface corresponding to S. Once again, if two surfaces are homeomorphic, their closed up results will also be homeomorphic. We can extend this concept to that of a connected sum. Given S1 cap and S2 cap as two closed surfaces or closed up surfaces, one can cut out a disk from each one and attach the resultants along their cut boundaries. The result is a closed surface S1 cap hash S2 cap called the connected sum of two surfaces. If you consider a torus, for example, and another torus, and cut out a disk from each of them, and then attach these two solids at these two boundaries, circular boundaries, take the union, what you would get would be the connected sum of two tori. Two questions here. Would this result, the connected sum of two tori, have any boundaries? And question 2, can this result behave as the bounding surface of a solid? You might want to think about them. Let's now study some basic surfaces and try to classify them. Basic surfaces can be of 4 or 5 types: a sphere, a torus, a Mobius strip, and a cross cap. A sphere and torus, some examples of basic closed surfaces. This is how a torus can be constructed. Take a rectangular piece of paper, join the two opposite ends to form an open cylinder, and then glue the two boundaries of the open cylinder together to get a torus. A Mobius strip can be constructed by a rectangular piece of paper in this manner. Take this rectangular piece of paper and flip this edge so that this arrow aligns with this one, and glue the two ends together to get a Mobius strip. This is what I mean. Take this rectangular thin strip of paper, flip this edge, and then glue the two opposite edges together to get a Mobius strip. A question: how many boundaries do you think a Mobius strip would have? Both you and I know that the number will not be 0. Are you thinking 2? Well, let's find out. Let me mark a point on this Mobius strip. Now what I'll do is I'll move my index finger and my thumb along the boundary from this point. You might want to follow very closely my finger movements. no matter what happens, my fingers are stuck to the boundary. What has happened here? I started with this point, started moving along the boundary, and I have come back to the same point. This would mean that the number of boundaries of this strip would be 1. Now let's look at some other basic surfaces. This is a clean bottle. Equivalently, it's also a figure 8 projection. Clean bottle and the figure of 8 projection. How do I get a clean bottle from a rectangular strip? Well, step 1, glue the opposite sides together to align these arrowheads. What you would get would be an open cylinder. And then take these two boundaries, flip them so that this arrow aligns with this one, and then glue these two opposite edges to get the clean bottle. Let me show this construction using a piece of dough. This is almost a rectangular shaped piece of dough. Well, I'm getting hungry by looking at this. Let's try to execute the first step. Join this and this edge together to get an open cylinder. I'm going to be a little careful here. My fingers seem to have gotten stuck. What you see now is like a two-ended open cylinder. Now what I'll do is I'll narrow down one of the ends . Since I have to flip or I have to ensure that this end does not get glued with this, I need to make a cut on this surface here. I'm going to be using a cutter. This operation is dangerous. Do not try this unsupervised. I'm going to make sure I don't cut my fingers. So I've taken this part off. I'm going to elongate the other end, bend it, and insert it through this hole. Look at the two glued ends now. Cut, take again. Look at the two initially glued ends now. They don't face each other. What I'll do now is I'll glue this surface to this one. I'll start with the glued end first, or the inserted end, and I'll keep joining the points. This solid looks like a clean bottle. Not as good as the figure that you see on the slide, but good enough for us to understand the construction. Note that the clean bottle or the figure 8 projection cannot be constructed in 3 dimensions without self-intersection. How do I construct a figure 8 projection? It is not going to be easy for me to show this in 3 dimensions, but I can just give you a hint. We have seen that a Mobius strip would have a single boundary. Take 2 Mobius strips and think of joining them together at the boundary. The result that you will get, or the result you will expect, would be a figure of 8 projection. Now let's talk about another basic surface called the cross cap. The idea is very simple to construct it. From a rectangular strip, try to join these 2 opposite edges so that these 2 arrowheads get aligned, and then try to join these 2 edges so that the 2 arrowheads get aligned. Equivalently, you can do the same with a disc. Take a disc, get it into the hemispherical form, and then try to join diagonally opposite points here. The result will be a cross cap. Let me demonstrate its construction. This is almost a circular shaped dough, a disc. First, I'll try to give it a hemispherical shape. It's not very stable, but it will work for us. Now what I'll try to do is I'll try to join 2 diagonally opposite points, and then this, and then this, and then this. I'll keep doing this to get a cross cap. Note that even a cross cap cannot be constructed in 3 dimensions without self-intersection. We now come to answering the main question we asked at the start of the lecture, whether it's possible for us to make a single statement about a variety of surfaces or solids that we see around. The answer lies in the main classification theorem. Every closed surface is homeomorphic to a sphere with some handles or cross caps attached. I'll tell you what handles are. But this is the basic statement or a general statement that the main classification theorem states for each and every solid around us. I'll demonstrate a little later what do I mean by a handle. But first, every single surface according to the main classification theorem is one of the following. It's either a sphere or it's a connected sum of tori or it's a connected sum of crosscaps. In solid modeling, we are not going to be worried about self-intersection in 3 dimensions. So we'll let go of this point C here. So for us, every single surface is either a sphere or a connected sum of tori. Now what do I mean by a handle? This animation demonstrates it. A torus is getting transformed into a coffee mug. The term handle comes from here.